So hello everybody, please let me know if you can hear me, plus if you can hear me, minus if there is some problem. Sorry for being late. This will be quite exciting model that we're going to build today, but I had a lot of things to cover today. All sorts of research work, plus tomorrow we have here in locally, if you know somebody in the high school who is who is interested in deep learning, tomorrow we have for high school students the deep learning contest. So it's like called Max Liga Intellect Olympiad. So it kind of took a lot of time from me, and that's why a little bit late. So please take a template from the 12.2 task. Let me check if it's okay. Hopefully it is. So 12.2 task template. Okay, we have only 2 people online. That's sad, but the model will be really exciting. I think in the beginning it was 3 people. Hopefully the one who left will return. But anyways, it's always better to be online here because you can ask the questions and I can help you out to understand it. Then later just watch and get it on your own. So 12.2 template ready for work, plus minus. If there is some issue with it, please let me know. If you're ready for work, then say plus, and then we'll look at the equations and the logic behind what we will look today. So we'll wait for some feedback and then we'll move on. As I say, this will be the first generative model that we will build together, so like truly generative. So you will see in just in a second really exciting properties from this kind of model. And nice that at least Armand is engaging. I appreciate that. We'll really hope that all of the people who are engaging with the chat and with the live sessions would be able also to complete the course. So some of the things. So with this template that we have, okay, maybe I should not start with the template. So let's not start with the template, but with the theoretical part first. So that will be also quite fun today, because this is really so this is not like your typical type of model. That it comes with a lot of like really good features for the future if you want to keep researching these things. So the one thing is that this looks like a simple autoencoder like we did last time, and actually in the homework I gave you basically the pre-trained encoder that generates the z vectors, and the z vectors in this case are the green samples actually. So the sample here that is written here as a sample, this is a z vector actually. So, and but in this case we have sigma and mu. Sigma and mu. On the sigma and mu, okay, I actually saw that some people had the same issue that Gintz is saying that the dataset download do not work. So you can try to change that to extended NIST, eMNIST. Maybe that will work, because some kind of server issues I think there are today. I hope, because the eMNIST basically should be kind of the same idea. Also, you could try to use the the fashion MNIST. It actually doesn't matter that much what kind of dataset, like it's like all of the MNIST type of datasets, they are 28 by 28 grayscale. But so I think you're smart enough to choose some other dataset from the Torch Vision, but we will do that later in a second. The eMNIST, yes, the extended MNIST is large, but the simple MNIST is small. So the fashion MNIST is small. I think you can try fashion MNIST as well as we did before. So that would be a really easy way out of this. But anyway, so let's keep talking about the model. So we have mu and sigma. Of course, if you see mu and sigma, automatically you should start thinking that this is some kind of probability distribution. And that is, of course, the normal distribution or the Gaussian distribution. By the way, this is also real fun and exciting. For these kind of models, you can use also other distributions, like, for example, Gaussian or beta, gamma. There are all sorts of distributions that you could try to use or invent your own probability distribution. So here, if this is just a normal Gaussian distribution, and the way how it also looks like, so let me get some image. So of course you have seen that already, in some other cases probably, is that you have these kind of curves. So if I plug in this equation from our model that we just learned, the sigma here, the standard deviation, and the mu here, right, and the x is something that comes out of our model, basically the hidden state at this place, this is x, and hidden state at this place, this is x. If we plug everything in, right, then we can also sample from this. So if we plug these things in, we will get this kind of curve. So basically, depending on the sigmas and mu's, we will get different kind of curve here, the bell shape. And if we then, sample like on random any like sample from the x here, we will get some kind of y here. And depending on the shape of this bell, we can get different kind of outputs of the probabilities, right? So this green one would be really biased towards -2 region, right? So the other one would be biased towards this short region, and the one would be with the large region. So the idea is here that the model do not learn the z vector itself. The z vector we get from sampling the probability distributions, but what we learn is the mu and sigma. And mu and sigma is not just a one scalar value, but that's a vector. And if we plug in vector here, we sample out a z vector, so everything works fine. So this is kind of the same autoencoder that we did last time. Last time we didn't have this part and this part. This time we have those parts. And those parts are kind of vectors that we plug into our equation. And then we do the random sampling. And then we generate from this random sampled z back the reconstruction. And the great benefit for this kind of model is that when you train it later, you can have the ability to explore all possible outputs in this range of these samples. So for example, maybe you discover that this particular dimension up here, this ball, right, is responsible for the width of the letters. Like very thick, very bold letters have values maybe around this place, right, and all of the thin letters have values around this place, and you can like even create kind of slider where you just change the kind of your sampling strategy and get out different kind of outputs. And all of this is like kind of, you will see just in a second, it is mathematically enforced. So you kind of force this model to be optimal of compressing all of your information in these two vectors of the standard deviation and the mean. And in that case, then they are actually working as your guide for the sample generation and using some properties of your z So that's kind of really powerful way how to do this, and we will look at in just in a second, and then we'll code it. So another way looking at this model, another nice illustration that I found somewhere. I think the link for this illustration is also in the links that I gave for the preparation of the workshops. By the way, if you actually read those links, the workshops should be a lot easier. So if you have some difficulty of understanding, please read those links. So the input here, the encoder, right? So this is a convolutional encoder. Then it produces the mean and standard deviation. And that we can use for the sampling of the z vector using the equation in the previous slide. But we have some problem there, because if we would just sample randomly from that vector, we cannot then calculate the derivative, the partial derivative from that vector, because it's the random operation do not have derivative, right? So there is a hack, it's called Reparameterization Trick. So maybe should I write it down somewhere if I don't have it somewhere. Maybe I have it. So it's also listed here on this small nice equation. But I will try to show you another way. So this is again from another source. I like this as well. So here the original idea that you have the mean and sigma, and then you sample randomly the z vector, and then you pass it to the decoder. The problem is that now we cannot really, like a random operation is not differentiable. We cannot calculate derivative for that. Sorry. And the hack that they invented, actually, so if you look at the dates, this is not that long ago. It's 2013. So you should be quite excited looking at these kind of dates. Like, and even later when we look at some models, all of these things are developed not so long time ago. That means that if you go in this research, either with my team or some researchers that we're working with, or your own research, you can find something new quite easily. So it's like there are a lot of great stuff that you can discover and develop with deep learning. So here the idea is that you have the sampling of the normal distribution, or it could be also some other distribution, but normal kind of works better. So you sample that one, and then you use the Hammond product or the pairwise multiplication here, the simple one. So this is not a dot product. This is just a very simple multiplication. Because in the equations, if you see just one point, that is a dot product always, and if you see this kind of sign, that means this is a pairwise multiplication. And in this way, the epsilon here, the actually random stuff, is right now becoming a constant. So, and if you remembered how the derivatives work, the constants do not like trouble us. We can go over constants here. Everything works great. So this is called Reparameterization Trick, actually here is all written. So that's the way how we can train it, how we can get our error from this side to this side. Hopefully that's clear so far. I really hope. So what about other things? Let me check. Okay, there are also some other hacky ways how you could try to get by without doing the reparameterization trick. So one would be probably if you run this part of the code like hundreds of times, and then calculate those means and variances, and then somehow like pass them through that part, but that would be not efficient at all. So, but anyway, when you train the model itself, then later you can just use the kind of decoder part alone. So, for example, if you trained it, you can sample from that mean and standard deviation variation, and then just get out really nice pictures from that alone. And it looks like something like this. Let me show you. So if we imagine that the z vector is two-dimensional, and it could be like it's there's no problem. You can have two-dimensional z vector, and then you could have something like this, but most likely not so beautiful. So this is actually the MNIST dataset, the one that you say that you have problems of downloading right now. So, but normally this should not be problems to download, because that's like, I think, the most popular dataset in the world. So it's like it has been for a long time since Coon, and it's kind of like just a way to go for that one. So basically, and you can see that. So if we have those z vectors sampled, so maybe these all are not actually the samples themselves, but they could be sampled from this distribution, from that equation in the first slide, using enter the mean and standard deviation in that equation, and then multiply that by some sampling strategy, or even there are like samplers already made for you. So then you can see that they are very smooth, like the way how it becomes from 1 to 0, for example. So 1 is shaped like that, and 0 is shaped like that, and you see that's like beautifully shaping back to that other part. And it's like gradually. So, and the way how the distribution is enforced, it kind of forced the z distribution to be optimal for not jumping around with all sorts of predictions. So I mean, with the simple autoencoder, you can have like 0 and then 1 and then 0 again and then 3 and then 3, 3, 8, 6, 5, whatever. So all of the value, all of the outputs that you get would be messed all over the place. That they would be still clustered in some way. There will be like small cluster of zeros here, there. But with the variational autoencoder, where we have the probability distributions, they are enforced to be optimal. So that's one thing. Before we start with the most important part about the loss functions for this thing, because the model itself, as you see, is very simple, right? The encoder, decoder, and the z kind of the previous z vector is split in two parts. So you can split your vector in two parts with no problem, right? But the loss function is the issue here. So, but before we go to the loss function, let's look at one other very exciting property for this kind of models. So here there are examples where you can use the pre-trained model. So if you train a model on images of people, right? Like there are data sets where you have like all sorts of like CCTV cameras and stuff. So, for example, you have the training data set, whatever, the peoples with IDs and stuff like that, and then you have some kind of some other data set that is not in the training, so it's not related for the training, and then you have another sample like query for. So this can be either a query, it can be enrollment samples. So you pre-train. So this is in two steps basically. You train it, and then you use it in production in inference. And in inference mode, all of these samples are something new to the model, but because the model is optimal in the sense of kind of, or close to the optimal, like kind of suboptimal of using the z vectors. So if you give the sample that it never seen with some person that you want to match in the data set that you never seen again, the z vector distances, like the cosine distances, for example, that I gave you in the homework in the last session, would get you out these samples that are exactly the same person, even though that person was never in the training data set. So that's really exciting stuff. Or you can even like generate maybe out, if this is the encoder part basically, but if you pass to the decoder part, maybe you can generate some possible like disguises of the people or something. So, but of course, these models that we're gonna look are not maybe that powerful, but in general, the way how they are trained supports that kind of features. So the other one is there is a Kaggle Simpsons dataset, and for one research I did the experiment where I trained it on the Simpsons, and then I used it on those Simpsons that are not included in that training dataset. And there's also fun where you see that the characters with the like spiky hair, like this one and this one, they are closer together. Then kids are closer together. Then Carl is up here, and then there is a Selma up here. So basically, really fun. And also, again, so this image that you see here, this you can get from the TensorBoard, the embeddings projector. So already, I hope you are excited that we already worked with the TensorBoard projector. So it's like a very small step if you want to impress me or maybe make a cool research, to just make that those z vectors are projected on that TensorBoard, and then we can have really nice pictures that I can show also other students, and you can do in your research work or studies or whatever. So anyways, or even in production projects. That's from one of the use cases. There are more use cases to this, so maybe I should show more use cases just in a second. If I started talking about use cases, I should finish talking about them. So another one is really cool functions like these. When you have very robust and stable z vector, you can find, for example, a person with no glasses, then find the person with glasses, then subtract arithmetically subtract that vector from the person that had glasses with the person that no glasses, and add that vector to this guy with no glasses, and you will get person with glasses. So that's really, I think, quite powerful and cool. And for the homework that I will give you, I'll also give you a model where you can experiment with these kind of things that is pre-trained with the variational autoencoder. Of course, you can get the same effects using the deep metric learning, the GANs, and all other things that also have, they are kind of similar behavior. So here's again cool thing. So you have a smiling woman, a non-smiling, like neutral woman. Then in this vector that you get from the subtraction, this is kind of encoded the information about the smile, and then you add that to the neutral man, and you get the smiling man. And even you can sample from that vector. So of course that vector is not really a vector, but mean and standard deviation, where you can sample all sorts of variations of the smile, you know. So that's kind of cool. And lastly, I just want to find one example from one of my experiments that I also will give you yourself. Just a second, and then we'll start coding. Before starting coding, we actually need to look at some equations yet. Okay, my GitHub is linked out. That is not cool. Logged out, just a second. So what was my CC variational autoencoder? So I made an implementation that I cannot find, which is funny. CC variational autoencoder. Oh no, I accidentally typed it in wrong. Yeah, I found it. So you actually can find in GitHub one of my repos regarding the the things that I'm just talking about. So this will be actually your homework, where I think in that repo I don't have the code for that, but in general this is quite cool. So you can, for example, select out from the samples just once, then calculate the mean, standard deviation, mean, and then do the sampling of this and get all sorts of variations of number 1, for example, or I letter. So that's one cool feature, and I think the coolest feature is actually having the arithmetics on the numbers itself, on the shapes. So here there will be another example. So you select from dataset 5 samples with 6s, calculate the z's, calculate the mean of that, then select 3's, calculate the mean of that z's, and then calculate the mean of both, and then generate the samples, and you will get something resembling 8 in many times. So again, this is not perfect because the model itself as well, right now that we are looking and doing in this classroom, is not, of course, the kind of state-of-the-art research type of things, but at least you could do state-of-the-art if you just go a few steps forward. So let's check the last thing missing here. So that is with regards to the loss function. So the loss function is a two-part thing here. So maybe I will drop it in step by step, otherwise it might be too confusing. So the first part is this very simple part that you already know. So this one is the autoencoder reconstruction loss, the mean square error, or the absolute mean error, or maybe even sometimes they use also the cross entropy or something, depending on the image and the way how you want it to train. If you're okay that the loss will never go to the zero, maybe it's okay to use like some kind of blurry images with the cross entropy. So here the first term is actually I don't like that sign, just a second. Call it just like don't like that it doesn't look like a loss. Just a second. So the first term is the mean square error that you already know, that is our reconstruction loss. And the second term is KL loss. So like Kuhlmann-Leiblich, or let me double check. By the way, that is not the only way how to do this. KL divergence. So that is for the probability distribution measurement, basically Kuhlback-Leibler. But there are also Anderson-Darling, there are, I think there's Smirnov or something. So there are quite a few metrics that you can use for comparing two probability distributions. By the way, I have not seen that much research in that direction. Maybe there is, but I have not seen it. If you know that, then please share to me. I will be very happy. But in general, that I think is exciting direction for research. Reconstruction. So this is the first one. And the other one is let me add the full name of that one. So that one also goes from the entropy, cross entropy type of family of functions from information theory. So I think you can kind of get those functions from each other at the end. There are some flavors of KL, so either it's like continuous or like is it the discrete probability distributions. The equations are very simple. At the same time, you kind of need to get around with them. So one thing is that there is you can have it actually in at least in two ways. So the P can be first and Q can be the second, or Q can be first and P that can be the second, and that kind of changes the way what kind of output you will get. Like in one case, the zero will be when it's matching. The other case, the zero will be when it's not matching. So it depends on what you want, basically. In our case, we want that one to be 0, basically when it's matching. So we will force the KL so that Z would be always the same. So that's really something to think about. So we want this to be reconstruction to be the same as the input, but at the same time we want that all of our Z's are exactly the same. So that means that we are forcing all of our Z's to be exactly the same. And how can we get the output? Like if we have the Z's as, for example, everything as that Gaussian distribution here in the first slide, like this blue one, all of our Z's look like that, then this is impossible to reconstruct this thing or something else. So this is very interesting loss function. This is the first kind of adversarial loss function that you see in this course. So the GANs and all sorts of things also, you work with these kind of approaches where you have two opposing forces. So you have the kind of the one force is the reconstruction, and other force is the KL that wants to get it cannot actually reconstruct anything because everything is crashed down to the same Z value. So the way how then it works in the training, actually, this is one image from one of the homeworks that I might give you. So I have quite a few of them. These are really fun. So there is one data set of the colored balls and the different sizes, and we want to reconstruct them. And you can see this behavior that's really nice. So that in the beginning, the KL loss goes to the 0, and the reconstruction is quite high. So basically, when it goes to the 0, I cannot reconstruct anything. So it actually looks something like this. So in the very beginning, all of our letters will look like blobs because the Z vectors are all the same and you cannot get anything out of them. And then at some point, the model understands that the only way how we can get this or this is to start raising the KL. So the KL rapidly goes up and then it starts going again down. And then at some point in the future, when it's like just before the next jump, that will be excellent place where to save the model, and you would get something really beautiful. So, but to the KL function itself, I mean the distribution depends on the probability distribution. So here the KL. One of these terms, so let me check which one. So the terms of the P in this case, the upper term, I think the upper term is, in this case, is the output of the model, and the Q is our prior, basically. So on our prior means that we're going to use some kind of known probability distribution that we want this to be matching. We want this to be forced, so that I want that the Z vectors always match this probability distribution and create those funny blobs, basically. So I want that Z vectors will always match this probability distribution, and this will be called our prior. And in here, for the prior, we also need to define our own sigma and mu. So we decide just like a hyperparameter sigma and mu. But by the way, like all of the variational autoencoders usually use just the so they use mu 0 and sigma 1, like almost every time. Like you can use something else as well, and I think that would be more fun. But like basically they use it in that way. And the last thing missing before starting to code is what actually is looking that equation when they put in the KL equation, what was this, the Gaussian equation, then we get out something like this. And here, depending on the direction, so here, okay, so here there is an integration of that equation because they chose this kind of form for that. And at the end we got this one. And here again, the sigma, basically what we have here, the sigma 1 is the prior, or the 1 basically in this case, or we can just call it sigma prior, and the mu 1 is the mu prior, and that is 0. Mu prior, that is 0. And the sigma 2 and mu 2 is something that our model generates. So that's great. That is about about this part. I think the only thing that is that if you then, so there is a 1, the 0.5 at that side, the sigma logarithm So I think not sometimes, but depending on the order how you put it, we might need to minimize or maximize it. And I think that like at least in the last time I checked, it should be in the front the minus sign here, or not, actually not. But there is something not, no, there's sigma, that is cool. And mu, oh yeah, it should be the same equation, except the minus, I'm not sure about the minus 1 divided by 2. So we'll check that one. But there is the flipping of the sign here, minus that part. I need to double check this equation, but in general, I think I will check that later. But I think that this one is correct. But we'll see. If there's something that's work, we can go back to this one. I'm not like, I definitely know that depending on the order here on these sides that I showed you, like we might need to either minimize or maximize this KL. So maybe we need a minus sign in front, but we will check that in the implementation in a second. Most important thing is to understand this behavior that we are trying to force the distribution that the z vector matches the Gaussian, and that all of our z's in the beginning look like this. They are same, and at some point they are starting to struggle and get out of the balance. And for that equation, after this session, I will double check. And the one thing also here missing, actually, I should add it. And maybe I will add it here. And I don't like that this equation doesn't match, but I will check it. Is that there is something called beta variational autoencoder. And I'll also show you some example of that. It's very simple. Basically, it's the same thing that this one, but the only thing is that we have the beta in front. I mean, the kind of not in front, but there is a beta coefficient. I will copy this one here. So the beta coefficient is just something that when you have a loss function, oh man, this is not what I want. So the loss functions, of course, they can have multiple parts, and they are called composite loss functions. And when you have multiple parts of the loss functions, it's sometimes better not to have the gradient like split out evenly, but maybe you would like to have some part more reinforced than other. And here you have a beta hyperparameter, just a scalar that you multiply with a KL divergence. And then the effect is really nice. So some of the examples that I can show you. By the way, it also depends on either you use a sum or mean. If you use a mean here, like in front, then definitely this is not going to be a B150 and B1. It might be B0.1 and 0.01. But still, the idea that if you have a larger beta, then you have a lot of z vector dimensions. So here we have, let's say, so we have 1, 2, 3. What do we have here? So this is a reconstruction. We have 6-dimensional z here. So this is a 6-dimensional z. Maybe I should somehow color it, because this is not obvious probably just from looking at this graph, but it is really cool graph actually. So let me kind of imagine. So this is a 6-dimensional z. So z with the shape of 6 dimensions, right? So if you have a large beta, or some like relatively large, it can be also 0.1, and this can be E-4, for example. And in that case, what you see is that it do not use these 4 dimensions, but it's very optimal, and it converts this small ball that is like moving in 2 directions just in 2 dimensions, and that is beautiful. You imagine you can have some kind of slider and you can like simulate the outputs of those two inputs, and everything is learned automatically by itself. And in this case, where you don't have a strong beta, it's a little bit more mixed together. So if you would look at simple autoencoder, then everything will be totally mixed together. There will be no any kind of nice like logic behind those dimensions. Here, when you have the beta encoder, autoencoder, variational, you have some kind of vehicle where you can get to something really beautiful. So of course, to train this is extremely hard, because you will need to search a lot of hyperparameters. You don't know if this is a 150, 0.1 or whatever. You know some range. So if this is a mean, then probably this is below 0. If this is a sum, then probably this is above 0. But the exact number depends on the data set. It depends on dimensions. You also need to search the architectures. You need to search the learning rates. You need to search the batch sizes. There's like all sorts of crazy things, but it is possible to find really beautiful model using this kind of loss function and architecture. So, okay, I've been talking for quite a long time. Let's keep coding. So, by the way, any questions so far? If you have some questions, please type in the chat, and maybe let's double check. So, is it clear so far? So, plus, minus. At least if something is not clear, then hopefully at least the idea of forcing the z to match the this probability distribution and then sampling for it, is it clear? So please let me know. And if it's not clear, then it'd be great if you add the slide number, or like have some small question with regards to what part is not clear. Meanwhile, I will look more at the equations that I shared with regards to the KL. Okay, there is one minus, but if it's not clear, then we need some kind of extra information, because like I appreciate that you participate and stuff, but like just a raw minus kind of not really helpful. But like if there is a lack of knowledge also in the basis of functions itself and the maths, so you can try to look at the like preparation materials that I gave you. So, but anyways, the loss function is this one. We will check about the KL equation. If something not work, we can flip it to the other that I showed. And the model itself is this one. And so this is the model, the equation, and the last thing is reparameterization trick with the sampling strategy. So we have 3 parts that we need to implement, and then we're good to go. So let's share the other screen. I hope you got the code already. So let's see if I use the MNIST. So I also created some snippet here to ignore other classes, to make it a little bit not so heavy model, and also added this one to check if there is a CUDA, then we have some kind of limitation of the, if you don't, like I don't have a GPU, that's why I don't want to use that big data set. So let's see, if I try to run it, we'll see if my network will download the MNIST. So now it's kind of working actually. Maybe it's actually quite large, but okay, I don't want to. This is fun actually. It's coming from Jan LeCun website. That is cool. I guess interesting how many requests he get from day. Like I mean, like probably hundreds of, like at least tens of thousands. So just a second. I will find somewhere where I have it already downloaded, but you can try to download yourself, or you can change this to the fashion MNIST, right? And you just need to change maybe some parameter here. If I go in fashion MNIST and see, maybe I even don't need to change, but see there's a like train download. I think that's the same exactly as for the MNIST, so it doesn't matter. But I want actually MNIST because those are the letters, or you can use the MNIST as well. But let me find, can I find my MNIST somewhere? Yes, I found it. So in my computer, I have this dataset located here. So I can copy it here and we'll see if at least I get it running. If you cannot download it, as I said, please try other datasets. You're already smart enough to know how to use the Torch Vision datasets. So at least from the homeworks, I see there should be, let's say, from the group at least like 4 people who should be able to do this quite fine. Like unfortunately, a lot of you are lagging behind. So we'll see that. Okay. So everything works except it crashes at the optimizer Adam. So that is because we have not yet implemented all of the code here in the to-dos. So first of all, we need to implement the encoder. So that can be anything you want actually. So you're already smart enough that you know that you can build your own encoders, right? Or we can use like some kind of predefined architecture. I mean like not predefined, but my architecture. So I can use one other architecture. Yesterday we made more modern architecture. Today we can make old style architecture. So this will be then the in channels. So if you would build your own model, I would recommend to use something that we used yesterday. So here we have out channels as 4, kernel size. The first kernel size should be bigger, right? Then we can use the torch NN, leaky relu. Then the batch norm. The batch norm needs to have the features. This will be the same as that one. So the batch norm, as I said, this is a little bit old style, but you can still use it. Like it's not old style in the case when you have like large batches. So if you can get 512 batch size and inside your GPU, then batch norm might be even better than group norm and others. So, but if the data is really big, then definitely not a good way to go. So here we can have another layer. So now what I mean by old school is that we will have 8 channels here, and we will start doing the strides. So let's have then there will be the, so this will be basically the same thing as for the max pool, but just using the convolutions, padding 1, stride 2. So now we reduce dimension by 2. So reduce dim by 2. I mean the width and height dim. Width and height, right? So remember I gave you the formula for calculating what will be the output with regards to the input, and that's fine. So it seems so the people say that there is some problem with the dataset. So I have an idea what I can do. So I will compress the dataset and put it on the Mega and give you the link. So no worries, you can use MNIST as well, not only the fashion MNIST. The dataset itself, it's 100 megabytes, it's not that big. So I will drop it in the Mega. and give you the link in just in a second. Okay, anyways, the mega is slow, but don't worry, it's like we can still write the code and then I will give you the link. Oh no, it worked, so great. Just a second, it worked. I have the extended list already stored there because I guess there was a problem of downloading that one because there's a high demand for datasets of the deep learning and that crash down the servers even. A lot of people want to learn this stuff probably. So let's see. Okay, I will give you the link in the chat, and then maybe I should add that also in the Google Classroom. So here there is the link to the dataset. So what I mean you should do is to copy that mnist inside your data folder when you extract it, and then show just the data folder root here, not the exact mnist root. So if you show it correctly, it will not download it anymore at all. So I give you the link in the chat, and I also will make sure that that link is added to the task in the classroom. So the mnist dataset, if not working download. That was a little bit surprising that the download didn't work. Anyways, so we can keep on doing the stuff. Okay, we have mom channels 8 here, of course. So we reduced dimension. Let's see, where did reduce dimension? Then we can add another layer where we don't reduce dimension. Again, yesterday I said that it's good to have some kind of repeating module, so we don't need to write a lot of repeating code. So today I'm just showing another way, but in general, it would be more preferable if you use some kind of repeating code and don't just copy a lot of these lines. But here, just to justify myself, I will start using different size of kernels in the middle of this stuff, so kind of trying to make it more fun. So, so basically, if you would build your own module, then you would need a lot of parameters here. So the batch norm like that will be fine. So let's say 8 to 6. So we need a 32-dimensional vector layout. That would be what I wanted to have here. So let's see, there is a convolution. So the 7 to the 8, then there will be a strided convolution and the batch norm. So this part, maybe I should add a new line so to make it readable. So like that. So this part is again what we split. Like only the channel count changes, so there will be 8 to 16. 16 again divided by 2, the width and height. There's a 16 again. So let's make another this kind of layer with the 16s. Actually, I don't like that this kernel size is. Oh, I guess I chose the 7 just because I don't want at the end to have not even numbers. Okay, let's leave it as it is. So 16 by 16, and here we could use 4, I think. So 16, 4, and the padding 1. Again, this is definitely not optimal. This is just something that works. Like if you plug in the numbers in the formula, at the end we should get the size that is 1 by 1. So that is the reason why I'm doing all this stuff. So at the end I want to have the size batch 32 1 by 1. That is what I want. So there will be the next layer. Again, the next layer will be the reduction layer. So there will be 16 to 32 to 4 to 2 to 32. And one thing that I must do before proceeding is to double check if everything is right. And then I will add this to the Jamboard so you can catch up. So if I had a breakpoint on lines 136 on the forward pass, run the debug, it should stop and give me the batch 32. If it will not do that, then it will be, you'll need to look where there is a problem, or at the worst case, I will start needing to calculate the width and height. Or other way is to use some hacks. So the hacks also would work. Let's see. Even if it will not be what I expect, I will use a hack immediately, I guess. Oh no, what is happening? Why it's so slow? This is not what I expected. I was thinking that this should be triggered more faster. Let's see again. So where did it stop? In image reading. Sorry for scrolling. I will stop scrolling just in a second. So let's see again. By the way, there is a parameter of noisiness. Okay, that is 0. That is good. So let's see. Why it takes so long to start running? That I don't like. Close other tabs. What could I do to improve the speed here? One option is to start running this on Google Colab. On Google Colab, probably you could train it better. But this is super strange. Why it's okay? Now it got to this. That's good. But super slow. Okay, now we got to this point, so that's good. Now we got to this point, that's good. And now we got to this point, that's good. Now it's working. Now it's working, right. Took some time to wake up. So anyway, out flat size is, oops, what we have in the size of that flat vector is 64 by 32. That is beautiful. 64 is the batch size. So that works great. Great, thank you for letting me know that it works for you. That is good. Any feedback is good, so we can move faster and more efficient. So, okay, the encoder part is what it is. So basically the same as for the autoencoder, nothing really special there. Like, you know, it's like so in this case, even I used just the convolutions without any average pooling and all sorts of interesting things. So here I dropped the encoder in the slide 10. Then the decoder we also will make using the old style stuff. But before that, we just have those two linear projections. So the linear projections are also something that could be more advanced. So right now I do just a simple linear projection, but this could be also sequential. It could be a model itself and make it like more smarter, you know. So like maybe let's make it 2-layer, 3-layer model. So here, out features 32. It could be also out features 2. If the out features would be 2, and then you could, I don't know, like scale it up later with other projections, then you could display it without any dimensional reduction algorithm on that nice graph that you saw before, where there is the 2 dimensions, and you can see how the letters changed from one to another. But you can do that also with dimension reduction, something like a principal component analysis. So, and then linear. So this will be again the same in features 32. If something not clear, please ask. If you can ask something specific, that would be excellent. So then torch and n conv transpose. So this is a transposed kernel. If you transpose the kernel and then more like, let me think. So I think like first of all, of course, you can transpose the kernel. Other thing is you just need to repeat it, and in that case, there could be also the checkerboard pattern. That is the problem for these kind of transposed convolutions, where we upscale with convolution, especially if you have stride larger than one. But yeah, still, as I said, this will be a little bit old school model. So 32 out channels. 16, kernel size 4, padding 1, stride 2. So this will be this. Then there will be the leaky ReLU. Again, the leaky ReLU just because a little bit better than the simple ReLU because there's no dead neurons then. At the same time, again, nothing magical, like leaky ReLU do not solve all other problems. So there is then 16 to 16, 4 by padding 1, and 16 as an out here. So that will be cool. Then the next one will be 16 to 8 with the same configuration as this one. 16 channels to 8 channels to 8 channels for normalization, so that everything is nicely around 0. So all of our like leaky ReLUs are happy. So the happy ReLUs are good ReLUs. So there will be 8. This one. So the kernel size 7. Let's make a happy neurons here. So happy excited neurons, not dead neurons on the 0 part. So there will be this one. On the negative part we have dead neurons, but with the leaky ReLU it's not, it's like half dead. So 8 to 4, kernel size 4, padding 1, stride 2, num features 4, then another convolution. Whoa, this was not a good one. Convolution, and the last one should be then from 4 to 1, the kernel size of 5, and there will be also a sigmoid there at the end. And let's have another reality check. I already did this, I think, a couple of sessions ago. Why we need sigmoid at the end? Why not use tan H? Why not 10H or nothing, or just for example the linear at the end, not nothing slash linear like the convolution linear con. So do you have any ideas? Like if no ideas minus. Because we talked about this already at least. I know at least like 2 or 3 times definitely. So think about what sigmoid output is, like what is the range in the y-axis, and why do you think it would be beneficial to use sigmoid here? Or maybe you have ideas what kind of other functions could be beneficial here. Meanwhile, while I'm waiting for the answer, I will try out if the model works. So the out flat is here. Then we have this kind of z vector stuff here. Let's see, it should work. I don't see any answers in the chat. Hopefully I will get some answer. So running the debugger, seeing if this part works or not. There is a breakpoint here that is strange. Maybe this is not a breakpoint but a bug. Okay, no, it works. So in the Y prim is the correct shape. So everything is great so far. So I'll drop this decoder also. By the way, again, like if you make your own encoder and decoder, I would be only happy. Like I mean, like if you will add in the homeworks or in the classroom works, the encoders or decoders or other parts that you made yourself, and you have some reason why you made it like that, I would be just happy to see that. So anyway, I see no ideas why we would need to use sigmoid at the end. So the sigmoid enforces that the output is always from 0 to 1, and our own data set is normalized to 0 to 1 here. You see there is normalization. The normalization is min-max normalization around like 0 to 1. It could be also -1 to 1 if we just like minus it by 0.5 and then multiply it by 2, or some other way. So you can standardize, normalize, whatever. And then if it will be -1 to 1, then there should be 10H at the end. And if there is like also probability distribution, that also might require either sigmoid or the softmax. But in this case, this is not a probability distribution here. So anyways, and the mu and the sigma that we have in the middle part here, the mu and sigma, they can be anything. I mean, like they can be. So I think the standard deviation actually should not be in minus part, but the mu definitely can be anything. So maybe we should limit also mu in a second. That is interesting proposal. I even did not think of it. So standard deviation should never be minus. So let's, yeah, that's a good point. I kind of did not see that, but yeah. So that we should add relu over sigma, so we don't get minus sigma. That is really nice addition. So we should definitely do that. So we will do that as well in a second. So these are just ways to limit the outputs to different kind of features that we want. And here, let's start then working on the middle part. So the middle part is quite fun as well. So we have out flat here. So we need z sigma. That is self-encoder sigma forward pass out flat. And then we need z mu. But I definitely advise to have over sigma torch. But I don't like that sigma is 0. So we could actually use the torch leaky relu. That's kind of interesting idea. But that then it will be negative. So I don't want to be negative. Definitely don't want to be negative. They could use absolute value as well, probably. Like there is not like a definitive reason what we should use there. Let's try. So this will be just a fun experiment if I just add the absolute value over this one. So because the sigmas should never be minuses, and I also don't like that a lot of like relu have long range of 0, and 0 also is not cool for sigma. So maybe even we could have relu with some kind of small epsilon. So or relu with epsilon. But again, the epsilon will be then the margin, so that will be a hinge loss. It will not help. So anyway, maybe ABS would be okay. But I'm not sure, like maybe it will not work as good. we'll see. So then the epsilon here is the, as in the equation, the normal distribution, and normal distribution over mean, mean of 0. I should add also here some comments. So this is just limitation, so we do not get minus sigma. So if you look at sigma equation, the standard deviation, it should not be minus standard deviation of 1, but mu of course can be minus. So size, so we wanted to sample something of the size of z mu. So what I mean by this is that it will sample batch with all of those 32 dimensions multiple times. So I mean, like, it will have the it will sample 32 dimensional z vectors that many times as samples we have in the batch device. So that's great. And then we have the only last small equation. So z is z mu reparameterization trick, right? So z sigma multiplied by epsilon, and this is a reparameterization trick. So just to make that epsilon is a constant that we can then include in our derivatives. So that should work, hopefully. I will add a breakpoint here and see. By the way, those like designs of a function, these are kind of really interesting. Okay, I see. Nice, thank you. Armans is giving a good feedback today. So Armans found a bug. And you see how easy it is to make bugs in deep learning, and still everything would work. So even if I not change the mu here, as Armand is saying, everything would work, but it would not work as we want it to work. So the loss probably would go haywire, and we will not understand what happens, but it's just the small typo there. So hopefully there will not be typo anymore. So the mu is fixed now. Thank you for the comment. That was really good one. So let me give you a cookie. It would be great also if you can then ask some of those questions regarding the logic that you did not get with the minus signs. That would be also great. But anyways, we don't have also that much time probably. So here the code is ready. I will pause that in the slide number 11. This is a little bit experimental because I added that absolute value. I don't know what will happen. I hope it will work great. We'll see. So then in the loss function, now this last step, not so difficult actually. We just need to write the loss functions, and the loss functions is something that is not that hard to do. So let's see. We'll have the torch mean. So this one you can write yourself with no problem, with middle of the night, right? Y minus y prime, so the mean square error, or you can write the absolute mean error or whatever. So and then the KL. The KL part, I think the equation that I gave you is definitely something not right with that equation. There should be a mu squared, just a second, mu squared, that is correct, plus sigma squared, that is correct. Mu, no, if I add the minus sign in the front, then there will be plus mu squared minus sigma squared minus logarithm of sigma. Something not right with that equation. But in logarithm I have squared sigma. If I add the minus sign in front of that, the minus of that one. So I will double check, but I think I need to add the minus sign in front of KL equation. But we'll see that. Like I think just from my experiments that I also have also in GitHub with more advanced models, I used the one with the minus sign in front. So in that case there will be z mu squared. Oh man, what is happening? Why there is so z mu squared, z sigma squared. And of course, this part is not difficult to fix. If there's something will be a problem, we can fix it easily, and I will update the Jamboard if something. So then the torch log of z sigma, it doesn't matter. The one can go also to the end. So z sigma squared. Hopefully, need to double check that one, but I think it should be okay. If there will be some problem, I will let you know and update the Jamboard. I will double check the equations a little bit later. But of course, if somebody wants, you can derive the equation and let me know if I have a mistake. So then there's a variational beta coefficient. So by default, beta coefficient I set as e minus 2. So because we are using the mean, that's why I use a very small beta. If I would use here the sum, in many papers you see a sum function there, and then the beta would be a lot larger. So wouldn't ABS be a problem if we get a large negative value for sigma? If I understand correctly, sigma should be above 0, but in this case, so okay, this is a good question in the chat, that if I add so this is really nice that you're thinking about these kind of issues. So basically so I will drop this in the Jamboard, and then I will go to the part where there is a question. I really like that in the live sessions you have questions and some meaningful questions, and also you check my code, so that's really great. You're like my debuggers. So anyway, here the ABS, so the large negative value would still give a good value. That is correct, and this is what we want actually. So we don't want we don't want sigmas to be minuses and then screw our probability distributions and then slowly get up to the correct range, and that just makes the training a lot slower. If I add ABS there, what you say, large negative value considered as good, that is not actually the case, because the z sigma is the output of our model. So I mean, what we could do is have here z sigma. We can rewrite this part as a torch and then sequential, where we have the linear layer followed by absolute layer, and that would be the same idea as having it absolute here. So the absolute value would have the derivative or partial derivative multiplied by chain rule to that following function, and that would solve the issue. So I mean, it would learn that it doesn't matter like if it's like large negative or large positive value. It will just produce easier the output that we desire. So if it, for example, by random, we initialize weights so that sigma in a very first run, the epoch would produce a lot of minuses. It would get as a pluses, and it would then not touch those minuses and start working around those minus values a little bit on the left and right side, and still get the best result faster. If we don't have here that ABS, I think most likely the sigmas would slowly go from negative to positive, but it will take a lot longer time. So that is my reasoning for that part. Hopefully it is clear. So it's just like the same idea of adding sigmoid at the end here. if we remove that sigmoid, everything is fine as well. So if I just comment out sigmoid, everything will work great as well. It will just take longer to get the results. So this is again the same idea here. Hopefully it makes sense. If not, please clarify. So let's see if it works. So if I run it. By the way, when it will work, I'm right now running on CPU with 200 samples, so I don't expect great results, but I just want to make sure that it works in general. So there is no errors in the sense that it works. So, and again, there's nice pictures where you can see the inputs and generated images. And even with those 200 samples, probably something would happen. So anyways, I will not continue running with 200 samples on CPU. I will try to run this on the Google Colab probably. So let's see. Also, I'm hoping that Google Colab will download the dataset. If it will not, then I need to download it myself or use another dataset. And this will be it for today. So I mean, like I will give homework in regards to the variational autoencoder. I hope that so far it's quite exciting and fun model. I mean, like you're gonna have like your first taste of GANs or like generative models or like energy models. There are all sorts of generative models that use similar approaches, like either implicit or explicit probability distributions. In this case, we have a prior here. We are fitting our z's to the normal distribution, but of course we could not define what kind of distribution we want to fit. So that is the case of the generative models, like generative adversarial models like GANs. So, and there are many flavors of GANs. Some actually are use also some part of variational autoencoders. So let's go to my cats in the Google Colab. So hello cats. So let's see, is the wrong button? Runtime, change runtime to GPU. And let's hope that I can download my dataset not to this location, but to this one. And connect to GPU node. It'd be nice to see some good curve here. I will definitely later check the KL equations. If I find some problem, I will let you know. But I think I trained those nice curves that I showed you before using the equation that we just implemented. If that's the case, I will update also Jamboard. Change the runtime, GPU. Right. Okay, so we got a training, so that's great. That's a first epoch. There's a huge checker patterns. That is what I was talking about. So the old style, these autoencoders with the transposed convolutions produce really nasty checkerboards. And what we have here is that we see that the KL is reducing, the reconstruction is quite high. So it means that like in the very beginning, the reconstruction is not good and the KL is dropping, so it's starting to fit to the same pattern for every single image. And I don't know, like maybe in 20 epochs or so, we will start seeing the same output for all of the samples, and then maybe in 100 epochs, we'll start seeing some differences, and then hopefully at the end, it would train something nicely. So, and also it might be that the parameters are not good, because we can see that train KL loss is basically very large value 1.4. The reconstruction loss is 0.3. So what it means is that right now it prioritizes the collapse of z vector, and you don't care about the output of the reconstruction. That's why each iteration do not give any better results. So, and this will continue happen until the KL will start to converge. And when the KL will start to converge, then the only way how to improve the result would be to reduce the reconstruction loss. Or another option is to reduce the beta. So you can easily see if I reduce the beta by order of 10, then the KL would be smaller and we would see nicer pictures sooner. So if I reduce KL to E-3, I will probably at this point already will see nice pictures, but the property of this probability distribution will be very weak. So I don't want too weak property, but I also want to have some nice pictures. So it's not an easy thing to train. I cannot guarantee that by looking at this for next 5 minutes we will start seeing something great. It's just that we need to run it multiple times and fine-tune the parameters so we get something great. So I don't know, maybe we can wait a little bit. Just to make sure that the code is running for all of you. So let's wait a little bit and see what happens. So it's still like, even on GPU, it's not magnificently fast. Especially this is a free GPU. If I run it on my own servers, we also have research like RTU have the supercomputer, and Ventspils University have some of the machines that you can use. If you run on those machines, you will get results faster. But on Google Colab, we can see them immediately like this, so that's also nice. If you would do this on your own machine, I would definitely advise to use TensorBoard, so you can browse it while it's running. So you start TensorBoard Listener while it's running. So the reconstruction loss jumped relatively but that is still on the test side. Oh no, the train also jumped. Okay, the KL jumped, so that's interesting thing. If the KL start jumping, that is a good sign. So that is a sign of something like getting out of that z vector. So there is like a struggle between the uniformity of z vector and the way to get out of the z vector some small bit of information that we can use for sampling. So we'll see. I think the KL is not reached its bottom. So when the KL reaches the bottom, then basically the output should be more uniform. Right now the output is kind of like too different for those samples in my opinion. So these kinds of training would be nicer to watch in high, like, what do you call it, like high speed, or what's like so it's slow motion, and then when you make the video much faster, because otherwise it will, don't know how long it will take. Be nice to see in real time some nice change, but the parameters, not sure if they are the best ones. The model itself also really rudimentary with the checkerboards all over the place. So wait. By the way, one thing that you see already here is that I use the same samples for every epoch to visualize them. So that those are the last samples from the test batch. The test batch, that's why I don't shuffle the test batch. I want them to be always the same, so I can compare the previous results from the previous epochs. how they look like. That's why this feature is nice, but we'll see. You definitely can see that the KL is still reducing, so I'm not sure. Maybe the optimizer is not smart enough at this stage. Maybe it should be, maybe the learning rate is too small or too big. Really hard to tell just from guessing. So the reconstruction is a little bit higher now. It means that, it basically means if reconstruction is higher, then the Z vector is more similar to each other. It kind of like, there's not enough information to reconstruct something. Maybe that's a good sign. We actually want to have, in the very beginning of the training, the variational autoencoders, to see that the reconstruction loss is high and the KL loss is low. And the images should look like the example that I gave you, where everything is very similar. And then, then when we get that point, we will start getting, again, something beautiful. So it just takes time. So if any of you train yourself on your own GPU something faster than looking at this thing, then maybe you can share some screenshot or whatever, or like in the chat, or add to the task in the classroom. I will definitely give some extra credit if somebody do something extra required from the tasks. So the output looks like a checkerboard. That could be, that could be. I mean, the Z, when the Z is all the same, it doesn't need to be that the output of reconstruction is always like a blob. It could be all like uniform checkerboard. It is also fine. So what I think I'm gonna do, I don't want to sit around and just look at these tables. So everything is happening, I think, in a correct direction. It might, I don't like that it's happening so slow. So I will just probably add to the Jamboard the final results of this training. If I wait for half an hour or something, what I'll get out of it. And you can share your results in the classwork as well. And for the homework, I will probably give something with regards to like vector arithmetics of these models. So I mean, like what I showed you in the slides of when you have pre-trained model, what you can do by combining the, let's say, the number 3 with, what was the, so at converged epoch, so you should run then longer. So try to run on 500 epochs or something, and also try to if you think that the KL is converged and the reconstruction is not good enough, but the reconstruction is then not reducing fast enough, then I advise you to. So let me show you. So what I advise to do is then, first of all, increase the epochs. So let's say 300, 500 epochs. Then the variational, the beta, try E minus 3, for example. Then you can also play around with the learning rate. Then, I don't know, let's say. Of course, you can play around with the model. You can play around with the batch size. There's a lot of things you can do. So, I mean, this is not guaranteed that it will work. Even if you run it like 3 times, it might be that it will not work one of those times or 3 of those times. So this is a bit like also depending on the random seed. It depends on the hyperparameters, definitely. So try out something else. The behavior right now is predictable. So this is good behavior. It's just that you need to get to the convergence. So I will share results later. I hope that the gist of this is understandable, why we need it and how it works. So I think it's quite a cool model. And we'll meet next week. The next week we will have work quite intensively on the time series. So this is like stock market predictions, weather predictions, whatever. And then the week after that we will have the reinforcement learning of that cherry on the top with the decision-making process automated by machine learning. And that's going to be it for the very basic course. There's so much more that you can learn here, but at least you have some nuggets to start